guidance today. First, we have a talk by Professor Sourav Chakraborty. Sourav is a professor in the Advanced Computing and Microelectronics Unit of the Computer and Communication Sciences at ISI. His research interests are in the classical and quantum complexity of Boolean functions, including property testing, sensitivity and block sensitivity of Boolean functions, and quantum database search, and electronic commerce, graph algorithms, and coding theory. He has very kindly agreed to give a talk on distinct elements in streams and Klee's major problem, which, as he says, has also caught the eye of Donald Knuth. So let's welcome Sourav and.
Am I audible? So thanks for inviting me. I mean, as I'm telling you, many people, there was a time when I used to come to Bangalore every 3 months, and now this is my trip to Bangalore after 5 years. And this is what COVID does to you. But anyway, so I'm very happy to be here, and I'm going to talk about this problem. I believe most of you have seen this problem and also possibly have seen an algorithm for that problem. And if you have forgotten that problem or the proof of the algorithm, it's a good reason. It is quite complicated. You need a lot of things. So what I will be presenting today is a problem that is an algorithm for this same problem, which we somehow by mistake found. And it's because possibly we are lazy. So anyway, so it's a joint work with Kuldeep Meel, who is right now in University of Toronto. When he did his work he was in anywhere Singapore. Vinodchandran, who is at Nebraska, and somehow Donald Knuth is at somewhere in India. So let's start with the problem. So say I want to design a web page, and I want to compute how many people are visiting my web page. How will I do it? Of course, earlier many of our web pages used to have that thing called counter. As soon as some clicks happen, counter goes up. All you need to is increment the counter. But the issue is that, but if I am not interested in just knowing how many people have just come, how many distinct people have come, how would I do that? So of course, one way is that what do you mean distinct people? For this talk, we can assume that different IP addresses from which people have come. How do I measure it? One thing is that, okay, we have to maintain the IP addresses. So if a 1 million visitor comes, I have to maintain 1 million IP addresses. When the 1 million and one visitor come, I have to come and check whether that person has come earlier or not, and accordingly update it. So the issue that happens is that the space required to store the information that I have to update in my backend is huge. Can I do something less? Instead of us, I'm hearing about myself. So, better? Yeah. So, can I do it better? In fact, maybe I am not interested in the exact count. What I'm interested in is the approximate count. What are the objectives here? It is that we should not use too much space. And when a new element comes, I should not take a lot of time to update my space. So this is the typical problem of data streams. Many of you are familiar with it. That an item is coming in a stream. An item comes, it's stored in the temporary memory for some time. According to that item, I update my internal memory. Then the item goes off. And I have no way of getting my pen memory. I am left with whatever sketch I have left with myself in my space, right? In the working space. And the job is to estimate and compute some interesting function of the stream. And again, just to formalize it, the goal is to optimize the amount of space, this space that you use for the workspace, and the update time complexity, the time required to process a single item. These two end up. So let me make my life a bit more harder. So the previous problem that I explained is what is known as the element distinctness problem. Here is a slightly more generalization of this problem. There's a very strong reason why I'm saying this, giving this problem. So here in the stream, a stream of sets are coming. So each item is now a set. And my job is to compute or estimate the union of the SIs. Estimate the volume of the union. Now, what we need to estimate with probability 1 minus delta, I want to do it within plus minus epsilon multiplicative error. So clearly, if the sets are of size 1, note that this problem is exactly same as the distinct element problem. Union of the sets, I'm assuming that by union of the sets, I mean only repetitions are not counted. So number of distinct elements. Right? Is this problem clear? So this is what we want to solve. Why is it different? It's like general set. I mean, S equals 1, it is exactly the distinct element.
The set contains
Excellent. Whenever you get a set, you can spread it up, open it up, and make it into a string of elements. Right? But then that means that when a set comes, the time required to process that set has gone up.
affects the update time, but not the
Yes. Affect the update time, but not the space. The goal is to optimize both what's the space complexity as well as the update time. Now, one thing that I've not told you here is how are the sets given? How are the sets accessed? And I'm not going to give you this formal proof till later in the talk, but I can give you an example. So this problem is a very well-established problem for last many years. It's called the Klee's measure problem. The sets are the axis parallel rectangle in higher dimension, in D dimension. So, of course, any axis parallel rectangle can be specified by just 2 points, right? The diagonally opposite points. The space can be given, so sets can be specified using just some D tuples, 2 D tuples in R. The number of elements, even if you are considering just the lattice points inside the sets, they can be exponential in D. Okay? And we are interested in the union of them. Okay, so this was the Klee's measure problem, special case of the set. Now, so this is the Klee's measure problem, formally defined. Exactly what I just explained. And now, what all things can I know about this Klee's measure sets? Let's think of it. Now, the sets are given, the sets are exponential size, but given implicitly using very small number of things. But in terms of accessing the sets, note that there are these 3 ways I can access the set very easily. Number 1, I can know the size of each set easily, not the union, but one single set in just polynomial in E and log of delta. So delta is the kind of bound on the universe. We can also sample at random from this set. And we can also check membership very easily. I mean, there might be other ways of doing it, but these 3 operations we certainly can. And whatever we are going to present will kind of be useful for this. So this Klee's measure problem, I mean, this work started in this mid 2000s, and it has been an open problem for quite some time. And by what we mean by open problem, the goal was to solve this Klee's measure problem for both the space and update time complexity of some polynomial in D and log N. So as Jalkumar pointed out, that if you remove any one of those two importance, in space complexity or orbit time, that can be done. Unlimited access time. And you can do the you just load this space, load this data, and at the end you will compute. And like, basically just maintain the whole thing. So it's only becomes interesting when you have both of them together. So poly, it is a log, it is a poly of log of the universe size. Universe size is of this delta to the power d. Log of the universe size is what is we are trying to. Log of universe size is of course the amount of information you need for even specifying the value. So at the lower bound of log of d log delta kind of appears. This was not. This is completely good. Now, coming back to the element distinctness problem. This has a much more interesting history. As many of you know, of course, I mean, here you are just set of elements are there, distinct elements are there, and you want to estimate the, so the if for this stream, 1, 1, 2, 1, 4, 1, 1, 1, 3 is the actual answer, and we want to get that epsilon delta approximation. And naively, you require a lot of space. Basically, you're going to maintain the whole vector of which all these things are coming. That, but there's a lot of work that happened over the last 40 years. And the kind of crowning jewel that we have now is that we have algorithms with this bound in this space. Note that in the element distinctness problem, the update time doesn't make any sense. So it's the one element only. Update time is not something of too much of a worry. It's only the space that is important. And this is seriously tight. I mean, in fact, it's tied up to constant. The constants are also pretty much. But this problem, this algorithm, has a problem. How many of you have seen this original algorithm here? One. And how many of you have actually tried to encode it? So the problem is that, first of all, this problem, the algorithm, if it is present in a normal class, it requires some non-trivial amount of concepts of hash functions and limited and independence and so on. And so that's one thing. But also, these algorithms are also not very fast in practice. Because, I mean, this is something I had no idea about. I'm not coming from a practical person. But later on, many people have told that they have tried to implement the algorithms, and hash functions, however beautiful theoretically it may be, they are super. They come with a heavy concept. Completely kills the purpose of it. So, in this talk, I will be first presenting you a very simple algorithm with a time and space complexity much inferior than this. I'm not even going to claim that I'm matching this thing. In fact, if you think of it here, in this case, there is no dependency on M. M is the size of the string. This algorithm is actually very interesting. Irrespective of the size of the string, space required is just depends on the log of the domain of the size, support size. In our algorithm, we will have a dependency on it. I will tell you later on how we can get rid of it. I will be presenting only this. This is what this algorithm is very simple. I will explain you and possibly give the whole proof of it. It uses only Charnov bounds, and that's it, nothing else. And I'm hoping that you are familiar with Charnov bounds, and if not, you will take it for granted. And this is the algorithm that somehow got the attention of Knuth, and Knuth wrote some nice thing for this. But irrespective of that, why is this algorithm interesting? Oh, okay, why is the algorithm interesting? I'll come back to that. So let me now jump and completely go in a different direction. The direction is actually how do I estimate volume of a something. So here is the picture that I've drawn. Okay, here is a bounding box, and there is some arbitrary things up there. Space. Now what happens if I try to estimate the volume of this blue area? Can you give me some way to do that? Randomly sample point. Excellent. Of course, there is an even basic one, which is just go and count the number of cells or something like that, but that's very expensive, going down one by one. The volume might be huge. The other one is just to randomly sample points. In other words, in some sense, I know this space. I know this space to be 100 square meter. Fine. I take this object out of my question and just randomly pick some points. I randomly pick 10 points and see how many of these 10 points fall in my blue area. Right? And if 3 points fall in, my estimate is that, okay, so 30% of the area, 30% of the whole outside area is there. This is how it is, right? It's exactly like if I say that in India, I want to estimate the number of people whose height is above 5 feet. I know the total number of people in India is 120 crore. How do I estimate it? I can randomly pick 10, 100 people, see how many people are above 5 feet, and I get this number, right? Will it always work? Let me give you another instance. What happens is now I want to estimate the number of people in India who is above 7 feet. Now what happens? Possibly the number is not zero. Number is a big number. It's possibly around 10,000. But it is still small enough that 100 samples will most likely miss all of them. My estimate will always be zero. But I want a multiplicative estimate. In English, not an additive estimate. Additive estimate is fine. Even if the number is 10,000, I want to report it within 1% error of 10,000. So this technique doesn't work if the size that you want to compute is much smaller than the unit. Right? So for in this case, what can we do? So let me give you another technique. Yeah. This will be the same issue. If the size of the set is very low, I mean that will work also. And this is a good set even when the set is size high. Randomly keep on taking points from the universe till the first one hits. By looking at the number of points, you have to choose if you have an estimate. That also will work only for when the sets are size high. Like in this case that I told you, you're randomly picking people, hoping that you get a 7 feet or higher person. Possibly you'll have to go on for no long. Maybe 1 lakh people for you. We have any assumption. We have no assumption. We have no idea what the assumption. And you're saying that I have no idea how to keep this set. It can be small, it can be large. So, but I have to be right always. Even if it is small, I should do it with 1% error. Even if it is large, it's all for one. This kind of thing will work for only for large. Small cases will not. Yeah, but that number still can be large enough. The actual number can still be large enough. Not large enough compared to the universe. Like the universe is of size 240. So, I mean, 2 to the power d by log you are basically. Shape your stuff. This is exactly hash. Okay. And that is what, in some sense, was done by the hash function. And I am not going to go into that. Very good. That's like how we can. Okay. There's a reason why I want to avoid hash function. You'll soon understand this. Okay. Whatever the technique that is there for hash function, you just think in your head that hash function technique will not work for steps. Huh? That is like this. You can do with pairwise hashing also. Basically, you just kind of partition the whole space into random places and then. Yeah. The number of hash functions that you're putting before you completely is someone. Yeah.
What we are doing is
No,
not
right.
that we mean complexity or
No. No.
feeling expected to think.
It's just I have no idea what we call this. You know, then this is a pictorial. We have to dealing with points in. Okay. So there's another way that I promised you. And that's actually a very easy way. Is that what happens is somehow I have a technique of picking every point from the set that we want to prove independently of probability something. So something like I am the government. I want to compute the number of people who are above 7 feet. I tell that okay, everybody is honest. Okay, you know whether you are 7 feet or higher or not. Excellent. You toss a 100-sided dice. If you get one, come and report. If there are 10,000 people, you expect that 100 people will report to you. I don't know how many people will report, but if the whole region, the expected number of elements that will be picked, or how many people will report, is the P, which is in this case 1 by 100, times the size of the region. If I see how many people have come and reported to me, which is this number, typically, I can have a good estimate of this one by saying the number of elements picked by 250. Now this is a good estimate. As long as the P with which you are picking up is bigger than 1 by epsilon squared. I know it. If P is 1 by 100, oh good, very good. Stand and all. No, the blue area. So epsilon is the error, the 1% error that I am allowed in the estimation. This is not in the chart, plain simple chart. You just do it and you will see that it is close. No complication. But again, I'm just so this is okay. Okay. So I'm trying to build an algorithm to estimate the size of the region, but I'm saying, oh, now pick everything with probability P, and I will not even tell you how to do that. But let's yeah. Now P can be less than 1. Then also it works. But the issue is that P is 1, like all the 10,000 7 feeters is going to come to me. I don't want that. I want to take less. Okay, so let me now tell you the algorithm. The basic idea is this, the Excel that's what I'm told, right? I want to devise an algorithm, a streaming algorithm, so that among this set of distinct elements, I want to feed every of them with probability. Now, not feed every element of this set, not the multi-set. So let's see how one can do it. So yeah. So I have the first algorithm. Okay, the stream is coming A1 to AM. I have a P. I'll come to the P later on, whatever the P is. And as soon as an element is coming, I'm putting it in my bucket with probability P. Do you think this is what? Yes, someone saying no. So that my goal is to pick every element of the set independently with probability P. No. Yeah. So it's like here, right? Say at some point of time, these green elements are the ones that have been picked in my bucket. Now a new element is coming. If the new element is this element, right? I'll pick it as one probability P. Makes complete sense. But if the new element is not this one, but someone which has already appeared, say this one, then what happens? This element came, I did not pick it up after tossing my coin, so it failed in some sense. Now it has come again. This time I have no clue about whether this person has come or not. Right? And so it's like getting a second chance of entering my bucket. Probability of it entering my bucket has now increased for this element. No longer P. Anyway, done. But if that is not the case, then we have no idea, right? So, like here in this stream that we had example, one is appearing, God knows how many times. And clearly, the first time one comes, maybe I reject. Second time one comes, I reject. Comes, maybe I accept. Then one comes, like one has been rejected 2 more times. And the third time it is entering. It's like giving a person multiple attempts to pass a course. So it's not going to do. The elements that are repeated more likely and more often are more likely to fit. So how do I avoid this? Let me explain you in another way. Okay, it is like very I've read of almost building up to something that almost is too trivial. Yeah, you have to understand. You have got it. That's all that we are going to do. So then this state, right? Among the state, the red points are the ones that have been sampled in my bucket. The blue region is the union of the sets that are there. Okay, let's say. And say I have lost complete knowledge of this blue region. I have no idea of the blue region. I only have knowledge that these things in my bucket are the red point. Now say a different set comes. New set arises. And my goal is to pick every point in the union with probability P independent. And it's like surprising that what the simplest algorithm is. And I'm too kind of ashamed to say that this is the main crux of the problem. Okay? The issue is that all you do is that these red points are with me, right? If I check if the red points are in the green region and check for those red points, and if they are in the green region, I throw them out. Okay. What happens? In that case, after I throw them away, the red points only in the blue minus the green region I have. So think what's there. Every point in this blue region has been picked with probability P independent. None of the points in this whole region has been picked. Now, if I can now pick points in this region independently, then the union of the species will do it. And that's it. Let's see how it translates to the algorithm. So the streams are coming. Okay. As soon as the element comes, irrespective of this is there in the bucket or not, I'm picking it up. Whether the bucket has that element has never come or the element has come 10 times, doesn't matter. At that time, the bucket does not contain that element. So its history is clear. And then you put it up with probability. This will ensure that every element in this set is picked independently. So that's what we have. Now one might say that, okay, what is P? I've not told you what a P is, right? So this is something, I mean, honestly, because I told you that this was the trick that seems to be missing from the literature. For how it missed it, I have no idea. Rest of it is like, I think will be a more standard fix for it. It's the adaptive, right? So you pick a P, but P, so P is too large, then the bucket size will be low. Bucket size will be P times the size on expectation, right? If P is too small, then it's not a good estimator. You have to hit the right level. What you do? You adaptively do it. So basically, say at this point, every element has been picked independently with probability P. But now, suddenly, after I did this union, I realized that it is overfitting my bucket. So what do? My bucket is full. Every element is picked with probability P. So what happens if I have this red and green points, dark points with me? What happens if I, for every point in this red and green stuff only, I go and toss a coin with probability half independently. So some of them get marked, I throw them away. If I throw them away, what's happening? Exactly like it has been picked with probability P and thrown away with probability half. So every element is picked independently with probability P by 2. So I can update my probability to P by 2. By throwing away my bucket, my space has gone down, so I am stuck with some more, I have more space. And that's it. This is the algorithm. With probability P, again, as soon as an element comes, I throw it away with irrespective of whether it is there or not. Else, we put it up with probability P. If my bucket suddenly hits the threshold level, I do a resampling and throw away each element in B probability half and update. P gets updated. Now, this is the algorithm. I think I have kind of convinced you guys that whatever we are doing, every element is being picked independently with probability P. Now, the proof of correctness of this algorithm is what is left. I have to somehow convince you that P can not go below that threshold. As long as P goes above the threshold, we are done. And I can give you the proof right away. How much time do we have actually? There is a top, so I don't know. Huh? 25 minutes. Okay, so I can go over this. Take me 5 minutes. Okay, so P is so yeah. Actually, I'm coming to that. I'm coming to that. We can now see that elements is nothing special. It can be done for tests. So, so say at some point, so I want to estimate, I want to have this bad eye. Bad eye is the event that the probability P at the ith iteration, after seeing the ith element, it's the first time it has dipped below this one. What is mine? And F0 is the exact number. So what is that probability happening? Now, let's forget all of this. Let me explain it here. So consider what's happened there, right? At the ith time, the element came, I picked it up, and it overshot the threshold. My bucket size overshot the threshold. So I pushed P below, and P below went below this. But what does it mean? Just before it came, what was the P? Was this twice of this? 2 by epsilon square F0. If at that time, if P was 2 by epsilon square F0, that means at that time, every element was picked with probability 2 by epsilon square F0. What is the expected number of elements that I should have had in the bucket? Is the 2 by epsilon square F0 times the F0 till that time, which is less than F0. The expected number of points in my bucket should have been less than 2 by epsilon square. But my bucket was full. What is the probability that my bucket is full when the expected value is 2 by epsilon? That's another turn of. And that's why we have a log m over here. The extra log m factor, the probability that I'm going, that is happening, that my bucket is overflowing when the expected value is less than 2 by epsilon square is 1 by m. And you do this, you do the union bound over all the i's. But let's not, what do you know? That's the actual, only one turn of that. There are some other technicalities that you can even after, even if P is high, I can still make an error. Because there's an error on the original term. So all of those errors. So let's come back. So we have this algorithm. It's not as good as what is known. A log m exists because of m. The log m is because we are storing each element. Okay? Because each element is like a sampling algorithm. When I'm deciding to choose one, keep one element, I'm keeping it fully with all the information. That was very different from the previous hashing algorithm, where you only store some partial information of that. So this membership check, like whether this new element is equal to any of the previous ones, could not be done. So good thing of this algorithm is that it is easy. Only a couple of attempts of invocations of Karnaugh bound gives you there. The algorithm is sampling based, and which basically makes it much faster implement. I will even talk about one such actual real life application that we see. It can be extended to union of sets. How the research went was completely in the other direction. We solved the union of sets and then pulled it down to element distinctness and wrote a simplicity paper for that. So what about union? union of states estimation? See, if you think of it, when I even gave the way of presentation, right? If you go back a bit, if this set is the union of the sets so far, and this green set is the new set that is coming in, all that I needed was what? That from this coming set, I need to check membership, right? And I need to sample from this set quickly. That are the only two things that I need. And that is what can be guaranteed from this set. So now before I go further, so I had explained you the these major problem. Let me explain you a bit more general problem. We call it the Delphic sets. So a class of sets is called Delphic if these following three things can be done quickly. Quickly meaning in log of the universe size. One is checking the cardinality of each set, something that was very easy in the case of rectangles, sampling uniformly at random, and membership. So there are lots of problems that fall in this category. Of course, the Klee's measure do come in this category. Think of another one, DNS. What is DNS? Or of the big problem of DNF counting. Right? So if DNF counting is, if I give you a DNF, how many solutions are there to satisfy? Each of the and basically gives you a set. That is that. All of n is basically union of the sets. Each of the sets have very nice structure. They can be easily computed in size. Sampling can be done easily. Membership can be checked. There's something called a Klee's measure, Klee's test coverage estimation problem. I'm not going into that, but actually this whole project started because some engineers wanted to solve this problem. I can explain you separately. Yeah, this solution actually gave us a engineering paper in IISc. Yeah. And this one is significant. Slightly better than. One thing that we are doing, I think, maybe this is exactly off the track, but many people ask us that how is it that you found this one? Nobody has found it. I think the biggest thing is that you think of the algorithm, there's a lot of reason. Throwing away of stuff. This is something we never encounter in our algorithm, either in Chakraborty nor in engineering. The throwing away of samples and throwing away of samples to ensure quality of sampling. That is what I think was the extra amount missing from this. Yeah. Okay, so let me go to. So okay, so our job is now we will be showing you how to do this union of set thing. Again, as I told you, it's basically everything is there except one. Everything is there. Okay, maybe this is. This one, the main idea is exactly the same as the singleton thing. In the union of the sets, you want to pick every element with probability. And every element is sampled with probability P, and this P has to be small enough so you adaptively change. This is exactly how was done in this. But Let's think of it. When the first step comes, big rectangle sequence, I have to pick every element probability. How far we do? I have a random access to this. That means I can get a random element from this. I don't need that. I want every element independently picked to probability. This is not hard. I mean, this is important not only for the first step, but it's every step that comes in any time. It's like, okay, so if a set is there, right? A big set is now. And I want to pick every element with probability P. Original set has say size 100. That means on expectation, I expect how many samples to be chosen? 100 P. Right? So what happens if I draw 100 P random samples from that set? That would have been the first attempt, right? But then that is not correct. Because in that way, the 100 P is the exact number of samples I'm going to pick every time. You think of it. Pick every element is probability P. That's not how it would happen, right? Exactly. It's not a Poisson. Number of elements that you pick has to be determined by the binomial. Because you will see that if you pick every element with probability P, what happens is that every element, the number of elements picked satisfies the binomial. If sample without replacement, for that you need another coupon collector, all of those things are fair. Right. Yeah. So basically you pick Ni from the binomial size of the set from P. This is also the reason I need a size. In the cardinal coefficient. And then I draw this many samples by drawing some more samples, this many distinct samples. Now, what happens if I realize that, oh, after taking this one, I am positive? I have got a lot of, like, Ni could be any number between 0 and size of Si. But even before I go to sample, I already know what the number I'm going to pick. If Ni is something that is making my thing overflow, I can resample from Ni, push it down, and keep on doing it. I don't even need to resample. I mean, I'm resampling the value. Ni is binomial. It's a nice thing that binomial composes. So, having said that, this is basically the whole algorithm. So, yeah. So, we got this algorithm. If this was the one that came out in Force 21, update time was this, and space complexity was this. If you think of it, so forget delta and epsilon, it's the log of size of omega, which is basically for the rectangle, it was d log delta, and the log m. The log m factor was there even in the Delphic. Now, I'll come back to this. I need uniform sampling, cardinality, and the membership is required to kind of do the removal part. Yes, that's also good. If you can sample every element with probability P, that's good. I mean, we have later on in some applications, we have looked into weaker versions, like what happens if I cannot have an exact size, but an approximation of size. Those things have been worked out, some of them, particularly if it comes from the I'll just talk about it. Yeah. So basically, using this one, we could solve this Klee's measure problem. This Force 21, Force 22. I'll talk about the Force 22 just now. This DNF counting, I mean, don't have the graph, but I showed you the graph. I was myself shocked. Like there's these worms that you draw, right? I mean, literally, it was lying flat. I mean, it kind of beat all the existing stuff hands down. So we have like the super fast DNA counting. Estimation coverage, this also is something. Even recently in our in Port 24, like this year, yeah, we have a paper on NFA counting, counting the number of strings of length K accepted by an NFA. It is actually an application of, but with the approximate. So just we wrap up now. So we had this, we solved this Klee's measure problem with the M hanging. We that gave us a new algorithm for the sampling list for element distinction. But if you think of it that okay, I have not done it very good job because the M still hangs, log M. How can you get rid of the M? Now, the actual algorithm that we have, you cannot get rid of it. I can give you an screen. Or so this M is not there because of our lack of, it's not shortage of analysis. But there is a reason why the M exists. See that the P keeps on going down, monotonically goes down. And it never, it can really make us lose it completely. That's why the M is required. But what happens, the idea is that what can we somehow make this P go up sometimes? And we could do it. The algorithm is much more messier. We could figure out how to remove log M. If you guys are interested, I can give you a slightly more cleaner button, which is under completion. But this, you see the dependence on log has gone back. Instead of log omega, it has become log omega to the power 4. So there is a latest update. It can be done to log to the power square. But that's all. So there is still a gap between log omega and log square. We don't know what to do. Okay. Donald Knuth, so my collaborator Kuldeep, so he had the guts to walk up to Knuth and told that, let me explain your algorithm. And Knuth somehow fell in love so much that he started writing an article. You can take out the article. Very hard to read. At least the first paragraph was very excited. And more importantly, he managed to make some small tweaks. So here, what was happening? Let's think of it. The hash function is there. The bucket size crosses this threshold. Suddenly, we go down from P to P by 2 and make a sudden move to half, right? That causes a lot of weird jumping around. Like the size of the bucket is like one threshold, other threshold by 2. What Knuth did is that he had a clever idea. Maybe I can talk about it offline. He just makes one more space in the bucket to put a needle. And the P doesn't go down from P to P by 2, but it goes down smoothly. Every element is picked with different probability. And using that technique, we could make this one unbiased. Our algorithms are not unbiased. But when we unbiased, expected value of the output was not exactly the correct. Excellent. And yeah, I leave you guys with this thing of open problems, like there is this log to the power 4, log square to log, that gap is there. And this technique actually has estimating of union of sets seems to appear all over problems. Thanks if you have questions. No, so good. So log omega is something that we got easy to get. We have a result in a submitted paper where we show that if you assume P is equal to it, actually more than that, some complexity measure, if you don't believe, but if you assume that, then you can have the algorithm go through for log. It means that chance of putting a lower bound higher than log is not. The only one way is that maybe if you can categorize somehow what is a sampling based. So the reason this hash function people could do it is actually they use the hash function very carefully. So even if they are storing, so if I want to make it log omega, I know that to store each element, I need to have log omega states. It means that I have to store on an average constant number of points. That's simply too hard to imagine that just by looking at constant number of points, one can even hope to get something. But in the case of hash functions, what happens is that you don't store the whole information. So somehow, if someone can marry this streaming algorithms, this sampling based technique and the hash function based technique, maybe this shaving of the log can be done. Yeah, yes. It's nothing is there in progress. I mean, like we have no idea how to your log. There are other measures that we are considering. It's a bit more complicated. F2 and all. Yeah.
Here, the set in and the second set in. You had parallel situation and see if you can find it from Meel. So first was running the sampling on their set state. Sourav. Then another person suddenly they realized they need to combine this, and they work their streams after having done this work.
No, not immediately because the membership is not. Yes. But there is, we have a submitted paper on in ORC on something can be, if you have some way to go back in one direction, you can do some lot of distributed things you can work out. But just the buckets union is not a like particular. If you have a particular same P, then no problem. You have every element with probability P. I have every element with fixed probability P. If you unionize it with multiplicity, then you can say that our things have been fixed with some particular P prime which you can calculate. No, there we are assuming that we are working on the same sets. You are working on the same stream. Oh, the completely different stream here. Then you have no idea. Then you have no. Something like this is not even. We did study some other stuff. We studied one thing called a forget model. So there is this streaming version where you can add and remove. It's called the turnstile model. Even for that one, our thing doesn't go. But if you can say something more stronger, that forget, so it's called forget model, that an element comes, so something like you are storing the information about how many people have come in your web page. And then suddenly somebody says that I don't want any of my history to be kept. So you have to completely erase that person's history, whether you have a sample or not. Then what happens? That's what that one is. It's unlearning. You can do the unlearning. This is also another thing that is coming out in Portland.